Anything else? Any questions that I might be able to answer? Okay. A couple of things that came up. People asking questions just before the break, or during the break. One of the things that I might have been less than clear about, I said this is measured, and it's measured because we've determined this equilibrium constant by measuring the forward and the reverse rate coefficients. So if that was less clear than it should have been, I apologize. But delta G at this temperature is measured because we've measured the forward and the reverse rate coefficients. I was also obviously less than clear about this slide here. So the experiment consists of, whoops. So the experiment consists of generating a hydrogen atom using the photolysis method in the presence of ethylene. And so this is the signal. So this is the signal coming from the fluorescence from the hydrogen atom excited using a resonance lamp before the pulse. And then we have a laser pulse that forms the hydrogen atoms, and then they decay away. They decay away to form an equilibrium. If it was simple and straightforward, then what would happen, if you can see, let me draw it out again. So we produce the hydrogen atom, and it decays away, to a non-zero value. And if it were as simple as that, then that would correspond to C2H5 at equilibrium. This corresponds to H at equilibrium. So the C2H5 signal, the H atom signal. Because there's the initial hydrogen atom concentration, H decays away, each hydrogen atom that reacts generates a C2H5, and so that is going to correspond to C2H5, that's going to correspond to H. And from the ratio of those, you can get the equilibrium constant. And the decay here, the effective rate coefficient is K forward times C2H4 plus K reverse. And so you get information from that as well. It's not quite as simple as that because the hydrogen atoms diffuse out of the region you're monitoring, and so that gives a loss of the equilibrated system, and so this curve decays a little bit. So it's not quite as simple as one might hope. This bottom line here is just the residuals of a fit to the experimental profile. So we plot the residuals in order to see that we're not doing a biased fit. So the fit is an unbiased fit to the experimental data. So that's what that thing looks like. Okay, this next topic is all about evaluation of rate data. One of the problems with experimental data in reaction kinetics is that it's often difficult to determine the rate coefficient accurately. You can sometimes determine it with high precision, but an accurate determination is sometimes not possible or sometimes doesn't happen because of complications occurring in the reaction system. There might be some secondary reactions that you haven't taken account of that are messing things up. And so if you take determinations that come from one laboratory and compare them with determinations from another laboratory, they may not agree. And the purpose of evaluation is to review the rate data that are available and to make a recommendation. And to make a recommendation not only for the actual value for the rate coefficient and its temperature and maybe pressure dependence, but also the uncertainty in those values. And so this is what I'm going to talk about for the next few minutes. So this guy, Don Balch, is a colleague of mine in Leeds, and in many ways he invented this process of rate data evaluation along with people at NIST. And this is an evaluation that comes from 2005. Don has now retired, and these evaluations are not really carrying on in this same sort of form anymore. But nevertheless, this still provides a very useful set of information. And the next few slides show you, are taken from an evaluation for a particular reaction and show you the structure of this, these sorts of evaluations. And this is done for many, many reactions. I strongly urge you to have a look at this, this journal and at this particular paper, simply to see what's going on. So the first thing is thermodynamic data for this reaction. So these are the enthalpies and entropies of reaction and the equilibrium constant. Of course, this comes from the early 2000s and isn't going to be as up to date as the ATCT data. But it does contain thermodynamic data. And here's a typical table for, sorry, I forgot to say what the reaction is. It's it's O plus OH going to O2 plus H. So it's the reverse of the branching step, H plus O2. So here are the determinations from a series of experiments done mainly in Cambridge and in Cambridge, England, and in Cambridge, Massachusetts. And what it shows are the measured rate coefficients at particular temperatures and expressions for the rate coefficient as a function of temperature here. And then at the bottom are reviews and evaluations. So these are not original measurements, but these are reviews or evaluations making recommendations on what the rate coefficient should be. Sorry.
The previous slide, there was a AC equation.
Yes.
Is that just their fit for their data? Or
Sorry?
is that just a fit for their data?
No, sorry, Kc, this is the equilibrium constant in terms of concentrations. So it's simply the equilibrium constant over this temperature range calculated from these data and the heat capacity.
So that's a standard formula?
That's a reasonably standard formula, yeah. So this table provides data on recent measurements and evaluations, including rate coefficient, temperature, references, and at the end is a link to the comments. And so here are the comments. So comment E which is somewhere here, refers to these measurements by Smith and Stewart. And I told you a couple of days ago about experiments by Smith and Howard, which are related to these. And so this is a fast flow system in which OH radicals were created by pulse laser photolysis at 266 nanometers of nitric acid. So that produces OH and NO2 in the presence of a much higher concentration of oxygen atoms produced in a flow system from the reaction between N and NO. And as we said a couple of days ago, you can work out the concentration of the oxygen atom because you're doing what's called a titration experiment. The OH was monitored by laser-induced fluorescence, and from the decays you can get the rate coefficient knowing the concentration of O. And there were measurements made over a wide range of temperatures, even down as far as 10 K, but there were large uncertainties down here, and so those were ignored. F refers to this line here, where the rate coefficient was calculated from thermodynamic data and the reverse rate coefficient for H plus O2. And then this is another expression, again based on the high temperature data. This is the central component of the evaluation. This is the recommended rate coefficient. And it covers the range from 250 to 3000 K. And delta log K is the uncertainty in the logarithm of the rate coefficient. So if delta log K were 0.3, that would mean that there was a plus or minus, if you like, a factor of 2 uncertainty in the rate coefficient. So the rate coefficient could be a factor of 2 larger or a factor of 2 smaller. So the uncertainty here is 0.2. Now, a key thing here is that this uncertainty is not based on any statistical analysis. It's a sort of feeling that the evaluator has about just how good this rate constant is likely to be. And this is a crucial point, as we'll come back to later on. So, and then at the end of the, no, not quite at the end, the next section is comments on the preferred values. It says the only direct studies in this reaction have been carried out at low temperatures, and there's excellent agreement between most of them. And although there be, so the experimental measurements only go up to about 500 K. Although there have been no direct measurements of K above 515 K, the reverse reaction has been extensively investigated at temperatures in the range 800 to 3400 K. And the preferred expression for K has been derived from a fit to the data obtained by combining the experimental data with the expression for K, H plus O2, and that enables them to go all the way from a couple of hundred K up to 3400 K. So the importance of thermodynamics here in making recommendations for this rate coefficient. And finally, it says the reaction has been subject to a number of theoretical studies. And in these evaluations by Balch et al., the theoretical studies were never used within the evaluation process. It was a relatively old-fashioned view, but even at that stage, even in the early 2000s, the theoretical calculations were not really good enough to compare with the best experimental data. But now that's all changed. And so here, finally, it gives you an Arrhenius plot for the experimental data, and it's fairly big scale, and most of the data scatter around this best fit line. Here's the reverse reaction, H plus O2, and the recommendation for this rate coefficient. So before this, there's a whole set of data about what measurements were used in this evaluation. And the uncertainty now in delta log k is 0.1 at 800 K, rising to 0.2 at 3500 K is the recommendation. It says there are no direct measurements below 500 K. The majority of the determinations of K have been made using shock tube techniques and generally in good agreement. There is a trend in the more recent studies to give slightly lower values of E over R than most of the older determinations. Our preferred expression for K is based on the more recent studies which are cited in the table. Okay, so that's H plus O2, and then this shows you the final page of this evaluation, which shows you all of the measurements that have been performed. And you can see that for this reaction, which is clearly a sort of centrally important reaction in combustion, there are many, many, many determinations. And what this gives you is the idea that there is a sort of probability distribution function of measured values which bracket the best fit line or the recommended line. But that distribution was not used in any way in determining the uncertainty in the rate parameters. Those uncertainties were simply the basis of a gut reaction by the evaluator. I should also show you this. Now, this is a slide that I showed you a few days ago, and I've slipped it in here as well. And these are the most recent determinations for H plus O2 by Hong et al. And Maston et al. These Maston et al. Values and the Pirali et al. Values were used within the evaluation, but not the determinations by Hong et al. And here's the recommendation from Hong et al., and there's the expression. And one of the things that I said was I referred you to this paper by Burke et al., which is a product of the CEFRC analyses. And what this paper does, as we said, was to look at many of the reactions involved in the hydrogen-oxygen system and make recommendations about them. And this paper from 2012 supports this value here over this range of temperatures from 1100 to 3370 K. So say at the bottom, see discussions on evaluation in later lectures, and that's what we're doing now. This again raises one of the problems with evaluations, and that is that we talked about the problems of updating things. These evaluations, these big evaluations at an international scale, that evaluation by Balch et al. Was funded by the European Union, involved people from around Europe, but also involved a couple of people from the US as well, so it was genuinely international. That's not really happening anymore. But this is a really important paper because it includes not only experimental work, but also theoretical work as well. And the theoretical work for this sort of reaction is now very good indeed. And for reactions in this hydrogen-oxygen system. Okay, here's another reaction. This is triplet methylene reacting with CH3, and this shows the other side of the coin. So this is a set of measurements dating back to 1975 with a range of values and a range of temperatures. I'll come back to that in a minute. This is the recommendation. What they recommend is a value of 1.2 times 10 to the minus 10 over this temperature range, constant over this temperature range, with an uncertainty of a factor of 2 in the rate constant. That's that's times 2 and divided by 2 in the rate constant, rising to a factor of 0.7 in delta log K, which is a factor of 5. So multiplied by 5 divided by 5 at 3000 K. Says there's considerable scatter in the data at 298 K. The rate data references 1 and 2, which were derived from very similar studies, need correction for the value of the rate constants from the methyl radical recombination used in the simulations. The reactions presumed to proceed via an ethyl radical. So triplet CH2 and CH3 come together to form ethyl, and then that falls apart because it's got plenty of energy in it, and it's not going to be stabilized. Significant temperature dependence is not therefore expected, but there could be one. The data may suggest a small negative temperature dependence, but the scatter at high temperatures is large, and provision of temperature-independent K is recommended with substantial error limits. To go back to this, these are two interesting determinations because this rate coefficient was measured relative to CH3 plus CH3. And the two papers were published in the same year, but they used different values for the rate constant for CH3 plus CH3. And that's why their values differ by a factor of 2. If you use the present best value for CH3 plus CH3, then you get a value of 7 times 10 to the minus 10 from both of these determinations. So they agree really very, very well. And this raises an important point. It's possible to go back to those old data and reanalyze them because there was a very simple process used to determine the rate coefficient, which was looking at two reactions that competed directly with very little else happening. If you go to some of the higher temperature data, a lot of it, again, dating back to the 80s and the 70s, they used complex mechanisms to interpret the measurements and hence determine the rate coefficients. But it's not possible, although you know the mechanism, it isn't really possible to go back and reanalyze the experimental data because the experimental data don't exist. They may exist somewhere in a file that somebody has, but they're not available electronically, they're not available on the web. And so it isn't possible to go back and reanalyze those data. And so there's a huge resource that in principle should be available, but it isn't. And what it does, the point that I'm trying to make here is that data storage is now very cheap. We can store data very, very easily, and we do in our own laboratories. But we ought to make it available through some sort of database, either in our own university or more centrally based, so that future generations, as our understanding of kinetics improves, can go back and reanalyze those data. Otherwise, those data are just lost. So this is a plea for some emphasis on storing experimental data. And I'm not the only person who's making this. Many people are making this sort of plea. And it's been discussed widely at the Combustion Symposium. If you go into the X-ray field, then before anybody is allowed to publish a paper that uses X-ray crystallography, they have to make their data available to other users. And perhaps we ought to be doing the same sort of thing here. So that was triplet CH2 plus CH3. Here's pressure-dependent reactions, a reminder of, so we talked about this a couple of days ago, and we said that if you take the simple Lindemann expression, it's not really very valid, and it needs to be, the curve needs to be modified by this parameter f, which depends upon So this is an expression for f, which depends upon another parameter fc on k0 and k infinity. So the overall rate coefficient depends upon three rate parameters: k0, the rate coefficient at zero pressure, k infinity, and fc, or f cent. And f cent is usually parameterized in this sort of form with t triple star, t star, and t double star as the fitting parameters. And so here is H plus C2H4 from this Bolch evaluation. And so here's K0, 1.3 times 10 to the minus 29 e to the minus 380 over T, or and these are expressions for both helium and for nitrogen, obtained from fitting over this temperature range. K infinity, here's an expression for K infinity, and this is over the range 200 to 1100 K. And then finally FC, now parameterized in terms of, sorry, I should have said more than three parameters, because there is this parameter A as well. In this case, FC is in terms of just two parameters, A, that's 1 minus A, and these parameters 40 and 1025, which give you the temperature dependence. And then here's the reliability, plus or minus 0.3 in K0, plus or minus 0.3 in log K infinity, and delta 1, sorry, plus or minus 0.1 in FC. And there's the page showing the plots of the data. Now, when this evaluation methodology was developed, there was no great call on numerical use of the uncertainties in the parameters. The evaluation panel simply felt that all they needed to do was to give some sort of indication of how good the data were. But increasingly, people need to use these uncertainties. So, for example, and we'll talk a little bit about this tomorrow, one of the things that you might want to do, should want to do, is to understand the uncertainty in model predictions. And that uncertainty comes from a variety of sources. In particular, it comes from the uncertainties in the individual rate coefficients. And one way of obtaining that model uncertainty is to do a Monte Carlo simulation in which you vary the rate parameters across the uncertainty range. So you have some distribution of probability for these rate coefficients, a probability distribution function for the rate coefficients, which tells you something about the uncertainty in them, and you select randomly from that probability distribution function in a set of simulations. And you repeat that many, many times, and that gives you a range of simulation results, and from that you can determine the uncertainty in the model predictions for a variety of things, the ignition delay, concentrations of given species, etc., etc. Now that approach is an essential way forward in understanding how good the model predictions are. But it's got to be based not only on good rate parameters, but also on good estimates of the uncertainties in those rate parameters, realistic estimates. And the approach that we've used we evaluation panels have used in proposing uncertainties is far too subjective. It is not an appropriate way of estimating uncertainties for this sort of approach where you're doing Monte Carlo determinations of overall uncertainties in models. So let me tell you about one approach to overcoming these problems. It's a sequential approach, which is going to take a long time. And I'll refer tomorrow to papers. So these are papers by Tomasz Tarani from Budapest. And I'll refer tomorrow to papers by Hai Wang, who has an alternative and somewhat faster approach to doing this. So the first thing that Tomasz did was to say that really we ought to be worrying about analytical expressions describing the temperature dependence of the uncertainties through a covariance matrix. So covariance matrix includes the standard deviations in the parameters, but also and the variance in the parameters, but also the covariances in parameters, the way in which parameters that you fit interact, and the correlations between those different parameters. So really what one ought to be doing is taking this sort of approach. And in this paper, recommendations are given for an improved representation of uncertainty information in future chemical kinetics databases using this covariance matrix. Tomasz's suggestions were not desperately well received by evaluation panels, but personally, I think it's something that we really do need to begin at least to think about and try to implement. And the methods are suggested for the determination of the covariance matrix and joint probability density functions for the Arrhenius parameters from the present uncertainty information given in kinetics databases. So let's have a look at what he's saying. So here's O plus C2H4. Here's the recommendations from this evaluation panel with uncertainties of 0.1, 300 to 1,000 K, rising to 0.3 at 220 K and at 2,000 K. And all Tomasz did was in this stage is to simply demonstrate what this means in terms of trying to get some function, some temperature-dependent function for the uncertainty and for the standard deviation. And so these are the recommendations that the panel makes, and this is some sort of fitting function through them. That's all he's doing here. For CH3 plus H going to singlet methylene plus H2, here's the recommendation, and the reliability is 0.15 over the range 300 to 1,000 K, 0.3 over the range 1,000 to 1,700, and 0.2 over the range 1,700 to 2,500 K. And this is simply because of the way in which the rate parameters were determined. At lower temperatures, there's the direct measurement of the reverse reaction, singlet methylene plus H2 forming CH3 plus H. And at higher temperatures, there's the direct determination of the CH3 plus H value. But there's this rather complicated set of uncertainties here. Now, this is the covariance matrix that I was telling you about. These are the uncertainties in the A factor. So taking this expression for a rate coefficient, the uncertainties in the A factor, in the temperature exponent, and in the activation energy. So there's the variance in the A factor, the variance in N, the variance in the activation energy. And then these are the covariances between A and N, and there's the correlation coefficient between N and E, etc. And the uncertainty in a given parameter is given by this expression down here. So this, if you like, is replacing those F values that we've shown previously, the uncertainty values that we've shown previously, where M depends upon whether you're looking at a 3 sigma or at a 2 sigma uncertainty. And so this is much more quantitative, The only problem with it is that the data simply aren't there in order to implement properly this sort of recommendation. But let's see how he gets on. So this is that reaction CH3 plus H going to singlet CH2 plus H2. And those are the recommendations that come from the evaluation panel. And in no way does he find it possible to reproduce that behavior using the sort of expression we had previously. And that reflects the non-quantitative approach which was used in making those original recommendations for the uncertainty by the evaluation panel. Now, that presents problems. It's very difficult to use the Tarani approach within an evaluation panel simply because the data aren't available. And so what Tamas Tarani is trying to do now is to step through a series of experiments and try to improve the representation of the uncertainties. And so this is the first paper of this new approach. And what he's doing is he's looking at just two reactions, H plus O2 going to OH plus O, and H plus O2 plus M going to HO2. And the reason for doing this is that, as we showed a couple of days ago, maybe it was yesterday, life is becoming a bit of a blur at the moment. What we showed was that if you look at that ignition diagram for the hydrogen-oxygen system, and you look at that third explosion or ignition limit, then that ignition limit is determined primarily by the interaction between these two reactions here. And so by looking at a variety of experimental results associated with ignition delays, for example, you can get really very precise information on the interaction between these two reactions. So this is the approach that he uses. First of all, the domain of feasibility of the Arrhenius parameters is determined from all of the available direct measurements. So these are direct measurements of these two reactions. And I'll explain what he means by this in a minute. Then the optimal Arrhenius parameters are then sought within this domain to reproduce the selected direct and indirect measurements. So he's fitting to both the direct values for the rate coefficients and also the ignition delays, or whatever indirect measurement he's using. So he's using both the directly measured elementary rate data, but also the data that comes from these indirect measurements, which are very sensitive to these two reactions. A new fitting algorithm and a new method for error calculation is developed to determine the optimal mean values and the covariance matrix for all the parameters. So this is what it means. Just let's concentrate on this slide over here, which is for H plus O2 going to OH plus O. And unfortunately, your stuff is in black and white, which leads to problems here. But the blue line there is the recommendation that comes from the evaluation panel. And the dotted lines, the dashed lines, show you the envelope of determinations. Okay? Anything that was way out was eliminated from this analysis. But what I showed you a few slides ago was that the bulk of the determinations give you this probability distribution function around the main line. And what they've done here is to take the maximum and the minimum values of that envelope of rate determinations. And so what he's saying is that any value that you fit must lie within this envelope here. Then what he does is he takes both the direct and the indirect measurements, and he fits to those using a Monte Carlo method and making sure that these rate coefficients stay within this range. And this is what he finishes up with. So the red line, the full red line, which is very close to the full blue line, is his new recommendation. It's very close to the original Balch recommendation. But the dotted lines are the new uncertainties. Okay? So that shows you that these uncertainties have been very, very considerably reduced by using proper statistical analysis and by using both direct and indirect measurements.
What were the uncertainties before?
Well, I'll show you that now. Okay, so here's so this is H. So the other set over here, which is somewhat clearer, is for H plus O2 plus M. And this is specifically for the low pressure limit. Oops. Okay, so this is H plus O2 forming OH plus O. And so here's the uncertainty parameter F from the Balch analysis. That's the initial uncertainty that Tirani uses. That's the envelope of these determinations. So that defines the maximum value and the minimum values that have been measured experimentally. And this is the optimized one. And so you can see it's considerably reduced compared with this uncertainty here. So the values for the rate coefficients haven't changed by very much. But on the other hand, the uncertainty in those rate parameters has been significantly reduced, and it's been determined by a better statistical approach to the problem. And that's what we get for the H plus O2 plus M, the low pressure limit. Now, the problem with this approach is that this really is an ideal situation. Those two rate parameters, the indirect measurements are very, very sensitive to those two rate parameters. And so what the analysis shows is that, first of all, the Balch recommendation is a pretty good recommendation, and it reproduces the ignition delays really rather well. But you can do a much better job on the uncertainty analysis. And doing that much better job on the uncertainty analysis is important if you're going to use this Monte Carlo approach to understanding the uncertainty of a model. And increasingly, that is what people are wanting to do, and increasingly what people should be doing. The difficulty, as I say, is that this is an ideal situation, but Tomasz is now moving on to other systems and gradually analyzing more and more reactions by looking at observations of both direct and indirect determinations. Moving on, you probably can't read this, but you can find this in his table. So these are the determined covariances of the rate parameters. So log A1. So these are the covariances. These are the variances coming down this line here for both reaction 1 and reaction 2. And then the covariances are the off-diagonals. And these are the correlation coefficients between them. This shows you the recommended values. And so these are the recommendations from Balch et al. These are values which have been used in a range of mechanisms that have been published. And these are the results of the work that Tirani has done here. And as I said, the agreement between the Balch values and this work here, the parameters look very different, but the agreement between the values is really quite close. So the central values aren't changing, but the uncertainties are better determined and are smaller. Yeah.
Are those parameters handling into the physics of the situation? So why do the parameters look so different? So like E by R, you would expect
Yeah.
E to have some physical meaning.
Yeah. No, the physics of the problem has not been used at all. These are just fitting parameters, and the differences arise because of the covariance problems. So it illustrates why it's important to know the covariances. So for example, if you look at the temperature exponent, n, then there's a very strong negative correlation between that and the activation barrier. So if you increase the activation barrier, you'll reduce n. I think that's the right way around.
Another question. So I think most of the data is under the low pressure. So I'm just wondering how to respond to the high pressure.
Okay, the bulk of the data for H plus O2 have been made at the low pressure limit. That's the problem. And the only paper that analyzes the pressure dependence in some detail is a paper by Troe. I showed you an experiment by Fernandez and Troe in which they looked at H plus O2 plus M in a high pressure reactor going up to about 100 bar. And even with 100 bar, you're only just creeping into the fall-off region of the rate coefficient. So what they would need to do, I mean, what would be ideal would be if there were some indirect measurements which were made with at very high pressures. And so those could be used in conjunction with the Troe determinations. But this particular reaction, H plus O2 plus M, is really quite close to the low pressure limit, except, I mean, at 100 bar, you're just beginning to creep out of it. So it's not too bad. Everybody okay? Okay, so I mean, so for example, if you look at 1,000 K, this determination here differs from that determination by a little over 10%. So the agreement is really quite good, even at the extremes of the range. Okay, I think that's all. Yeah. Any questions before we break?
It appears this method is based on experimental data. So what's to say that the experimental data is good? Or another way of looking at it, how does insertion of experimental data translate into this method?
Okay. The uncertainty in the experimental measurements, some people take a lot of effort to quote those uncertainties. Some people don't bother to quote any uncertainties at all. The great thing about these reactions is that there are many determinations. And so what happened in the evaluation was the central values were taken without any reference to the uncertainties that were quoted. And for these two reactions, that works pretty well. For other reactions, you really ought to be taking account of the uncertainties. And it's incumbent upon us all, really, to do a proper job of quoting uncertainties, both statistical uncertainties and also systematic uncertainties. Okay, 3 down, 2 to go. It's time for lunch.